starting from this trivial equation, the probability of A and B equals the probability of B and A. We can replace both sides with the rearranged formula for the conditional probability and write the probability of A given B multiplied with PB equals PB given A multiplied with the probability of A. Rearranging this a little bit gives us the Bayes theorem. PB given A equals PA given B times PB divided by the probability of A. The individual terms here have common names that are commonly used. The denominator PA is a normalizing factor to make sure that the product of PA given B and P given B and all the possible outcomes here are normalized to unity. A useful interpretation for the individual events is we can equal the event A to the data that we have at hand, and following from the data we try to derive a model, for example. So what is the probability for a given model given the data? The probability of B here is called the prior probability, which can be changed by additional data, can be altered by experience. Experience is expressed by this conditional probability, which is called the likelihood. What is the probability to observe the data given a certain model? Assuming a certain model is true, what is the probability to find the data? This is called likelihood. The left-hand side, PB given A, is called posterior probability. This is the state of belief after the data has been analyzed. We can reformulate also the previous slides when we have a set of events H1 to Hm, which are pairwise disjoint, such that the sample space satisfies the following equation, that the sample space is the union of all the individual events. And let's say an event corresponds to a certain hypothesis. There might also be an event E that gives us some information about which hypothesis is correct. We call E evidence. And before we receive the evidence, we have a set of prior probabilities, P, H1, H2, and so on. And therefore we know the probability of an evidence given the Hi, but we want to find the probability for the hypothesis given the evidence, and we can expand the Bayes theorem also in this form, where the normalizing factor is expressed as the sum over the conditional probability PE given all the HKs times probability HK and then summed up. Let's look at an example. Again, we are drawing colored balls from an urn. Let's say we know that, let's say there are red balls and white balls in an urn, capital R red balls and capital W white balls. If we know R and W, we can compute the probability of drawing 3 balls, 3 red balls and 2 white balls. If we draw with replacement, the probability is W over W plus R to the power of 3. W plus R is the total number of balls. W is the number of white balls, times R divided by W plus R to the power of 2. So this is simple, but it is usually not a problem a researcher faces. usually we do not know R and W. We can draw from the urn and note down the number of red and white balls, but we have no idea on the probability of drawing a red or a white ball. So that's the inverse problem. And this corresponds to, say, an astronomical experiment where we draw a sample of objects from the sky survey and try to infer from this sample how these objects are distributed throughout the universe, what properties they have, and so on. But from the previous slides, we now know that the probability of having the certain contents of the urn given the data is related to the probability of the data given the contents of the urn. So given some assumptions, we can calculate the right-hand side. So again, let's say there are R red balls and W white balls in the urn with a total of 10 balls in the urn. And let's say we draw 3 times with displacement and get 2 red balls. Can we say how many red balls are in the urn? The probability of drawing 1 red ball is R divided by W plus R, which is 10, but we don't know R. But if we knew it, the probability of getting non-capital R red balls, the likelihood is given by this expression, so that's R out of 3, so 2 out of 3 draws of this probability for drawing 1 red ball to the power of 2 times the probability of drawing a white ball to the power of t minus r. So this is the number of permutations of R red balls from t draws, given here by the binomial coefficient. And this is the probability to get our data, namely 2 red balls and 1 white ball, given our model. Our model is given by these 2 expressions. And what we still need to do is make an assumption on R and W. It can be that we have 0, 1, 2, 3, 4, 5, maybe up to 10 R red balls. And the number and R is the only uncertainty because we know it's 10 balls in total. We don't know how many balls we have, how many red balls there are. So we start by assuming it is uniformly likely that we have any number between 0 and 10 red balls. The probability distribution of such a uniform probability is 1 over R plus W, so 1 divided by 10. From this we can write down the posterior probability, which is proportional to the likelihood times our prior, which is this. This product is not yet a probability, because for a probability we need to make sure that it is normalized to 1. So what we have to do is we have to divide this expression by the integral over all possible r's, which is this expression. And here I left out the constant factor, which goes into the prior and also goes into the integral and then cancels out. Now this is the same expression, and it's actually possible to perform the integral, which is just R plus W, the number of balls in total, divided by 1 minus t, which was the number of draws. This is the integral of this probability of this expression here. So when we divide this by this number, we finally have a probability distribution, a probability, and from this we can then compute the posterior probability that the urn contains R red balls. And when we keep to our example, let's say we drew 3 red balls out of 5 draws. Then the red curve here gives me the probability distribution to find that we actually have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 or 10 red balls in the urn. It is centered at 0.6, so 6 out of 10, which makes sense because we have 3 out of 5 draws. It is 0 at no red ball in the urn, which makes sense because we drew 3 red ones out, so there are red balls in there. But we also drew 2 white ones, so it cannot be 10 red balls in the urn. So this expression normalized by this automatically reproduces here the logic that comes from our likelihood. But recall, we still do not know how many balls are in there. We know that with a probability of 20% there are 6 red balls in the curve, but it is only a little less likely that there are 7 or 5 red balls in the urn, and we could have got the same experimental results. So what we have here is a probability distribution basically on the probability of getting a red ball. If we would have performed 50 draws and gotten 30 red balls, this is the same ratio here, but it is to get 30 out of 50 makes our probability distribution much more narrow, centered around 0.6. So it gives our probability distribution a much more defined shape. It's much more unlikely to have 3 or 4 red balls in the urn when we get 30 out of 50 draws red, while when we only drew 5 balls, having 4 red balls is still not an unlikely scenario. The Bayesian probabilities sometimes lead to somewhat unexpected conclusions. A very famous one is when we consider a clinical test. Let's say we have a population and 1 out of 1,000 in our population carries a certain disease. We want to test whether a person is carrying the disease, but our tests are not perfect. And the probability that somebody with the disease tests negative is still 1%. But the test is also not positive for carriers of the disease, so the probability that a non-carrier tests positive is 5%, which means we can also assign a positive result to a non-carrier. Now let A be the event the patient is a carrier and B the event the test result is positive. We now have the 4 possibilities. Somebody is a carrier and has a positive or a negative test. Somebody is not a carrier with a positive and a negative test. We are given the probability of PA, that's the probability of being a carrier, and the probability of PB given A, which was the 99% coming from this one, and the probability of PB given not A, which is this 5%. Now let's look at the question. Somebody just got a positive test result. What is the probability that the patient is actually carrying the disease? We are looking for the probability of PA given B, the probability of being a carrier given that the test is positive. Applying our definition from the Bayes theorem, this is the probability of B given A times the probability of A divided by the probability of B, which can be expanded into these two individual cases, namely PB given A times PA plus PB given not A plus times P not A. And we know all these probabilities. When we fill them in, we find a probability of about 2%. Somebody has a positive test. The probability that he actually has the disease is only 2%. Now let's imagine you just got a negative test. What is the probability that you are actually a carrier? We can again set up our probabilities such that on the right hand side we have only the numbers, the probabilities that we know, and now we come to the probability of 10 to the minus 5. So when we get a negative test, it is very unlikely that we are a carrier, but if we get a positive test, we still can keep reasonably calm because there's only a 2% chance of actually being a carrier. Now with these conditional probabilities in mind, let's revisit our supernova example again. Remember, we were asking what is the probability to observe a naked eye supernova given the data from the previous centuries, which was 4 supernovae in 10 centuries. How can we use our Bayes theorem to estimate the probability to observe a naked eye supernova? How do we estimate this? The Bayes theorem consisted of different terms. We had the likelihood, which we translated into the probability of the data given a certain model. The model here in that case is a supernova rate, the probability that a supernova happens. The probability of ρ, the supernova rate, is our prior probability. That's the distribution for all the possible choices of ρ. The probability that the supernova is ρ given a certain data is the posterior probability and actually the answer to the question, how many naked eye supernova do we expect? This is the wanted result of our analysis. And we have P data, which is the evidence, which is the normalizing factor in the Bayes theorem. So the probability for a certain supernova detection rate given the data can be computed like this. Let's take a look at the individual factors. Let's take a look at the likelihood, the probability to observe a given data given that we know the probability. And a good model here is the binomial distribution, because we are asking what is the probability to observe a certain supernova in a century. So the experiment is either we have a supernova in the century or we don't. If we know the supernova rate, we can then compute the probability to observe 4 supernovas in 10 centuries, which is ρ to the power of 4 times 1 minus ρ to the power of 6 10 minus 4. And we have to multiply with the possible ways to combine 4 out of 10 supernovas, which is 4 out of 10, the binomial coefficient here. So with this likelihood, our posterior probability is the likelihood times our prior on the probability for a supernova. And in the absence of any more detailed knowledge, let's assume that any probability between 0 and 1 is equally likely. That's minimum knowledge. So the probability is then for uniform probability 1 divided by the difference between the maximum and the minimum possible way result, and this is 1. So we just have a 1 here. To make this into an actual probability, we have to make sure it's normalized to 1, which means we have to compute the integral of this for all values of ρ and divide this expression by this integral. Then we are sure that it is normalized. This expression, the integrand here, can be integrated into, so this is a constant, the binomial constant goes out, and we just integrate this here, and this can be expressed in terms of the beta function, which is a combination of gamma functions. A gamma function can be envisioned as the generalization of the factorial for non-integer numbers, and the beta distribution can be expressed in terms of this gamma function. So in general, for n supernovae in m centuries, the distribution is given by this factor, which is here this one, divided by the beta function for n plus 1 and m minus n plus 1, and the binomial coefficient cancels out. Let's take a look at how this expression, how the posterior probability distribution looks like. We have here 4 supernovae in 10 centuries, and this expression looks like this. It is nicely centered at point 4, which reflects the fact that we observed 4 supernovae in 10 centuries. If we had 5 supernovae, it would be centered at 5. If we had 6, it would be centered at 6, 7, 9, and so on. If we had 10, no, if we had 9, if we had 10, it would be centered at 10 and look like this here. If we had not 10 but 15 centuries, it would consequently shift to the left, and it would become narrower and narrower. This is the same effect as we already had in the urn example by having more draws.